Hello everyone, hope everyone is doing well. So today we will see lecture number 14 from design and analysis of an algorithm. Today's topic is, as you know, we are learning and understanding how to calculate the time and space complexities. We did linear search in the last example. Today we will see binary search. You know that in linear search we have to search the element sequentially, but that is time consuming. It takes much more time if the element is present at the end of the list. So that was a disadvantage of linear search. Now in order to overcome that, another searching technique came to us and is called as binary search. Say here we have a list of elements. We know the first element is represented with low, the last element is represented with high, and we find the middle element. How we find the middle element? We add up the indexes. This is a 0th index, this is the 8th index, divided by 2, that is obviously 4. So that is how it came the middle element. Now say for example in this list we have to search the element 19. Now we have to see, is 19 greater than or less than the middle element? Obviously 19. And in binary search our elements should be in the sorted order, but in case of the linear search it is not necessary. For binary search it is a necessary condition. We cannot have the unsorted list of elements. So we have to search whether this 19 is greater than this middle element. If it is less than the middle element, then we have only to search the element in the left part of the array. And if the element 19 would have been, there would have been some other element, and that element would have been greater than the middle element, then we have to search the element in this part of the list. Now in our case we know it is 19, so if less than, so now we only have to search from index 0 to 3. That means we know that 19 is less than 33, so we have to search it in this list from the index 0 to 3. Now this part of the list has been discarded. Now this will become, the index 0 will become low for us and the index 3 will become high for us. Now the middle of 0 and 3 is 1, because 0 and 3 divided by 2 is 1 point something, so that is how we calculate it. Here 19 is greater than 6. If we have to again calculate the middle element, that means 0 plus 3 divided by 2, which will be 3 divided by 2. It will be 3 something, 2 ones are 2, this is 1. We don't have to consider this, so middle element will be this point at this time. Now again we know that 19 is greater than 6, so we only have to search it in this part of the list from the index 1 to 3. And finally again we will divide the list into two halves, and obviously we will get the element in the middle. If again we will divide this will be 3 plus 1 is 4, 4 divided by 2 is 2, so we are going to get the element. This is how binary search works. Actually this is the algorithm for this. Int array, int n and int value, int low is equal to high, high is equal to n, int mid. So we know that if lowest, that means the lowest index is less than or equal to high. If it is less than or equal to high, that means we have to return it, there is no element present in the list. Otherwise what we have to do is we have to run a while loop. Okay okay, no, sorry, while low is less than or equal to high, we have to run the whole list जब तक कि हमारा जो ये लो एलिमेंट है इस हाई से छोटा हो या बराबर नहीं है. If it is greater than high, then we have to stop, because there would be no element in the list, or that is what we call as the bound checking. So this is the what we say, the algorithm for this. We found the middle element by adding the lowest index plus highest index divided by 2. We find that if value is equal to the middle element of the array, then return mid, because that would be the best case for binary search basically. If not, then we check if the value is less than the middle element. If yes, then the high will be equal to mid minus 1. That means we only have to search the first half of the array or interval. Else low will be equal to mid plus 1. Or if value is greater than a of mid, then we have to search the second half of the interval of the array, or else return 1. Now, how to analyze this and how to find the time complexities? When the first time we are finding the middle element over here, okay, how many comparisons we do only one comparisons with the middle element. We always have to compare only the middle element. When we have to compare only once, how much data is left to us where we have to search the element, that's n divided by 2 items data left. And that is what best case of binary search is. If we didn't get the element at first by dividing the array into two halves, then obviously we have to perform two comparisons, and at that point of time n by 4 items would be left to us, like this. If this is an array, okay, 1 to 2, we are dividing this array. If we will get the element, that is the best case. If not, either from this side or from this side, again we have to divide this. That means we will perform the second comparison. If still we didn't get it, array is so long, we have to perform 3 comparisons. How much data is left? N by 8 items would be left. N by 8 means, that means our element with n number of our list with n number of elements would be divided by 8 parts. When 4 comparisons, and n by 16, and so on. So similarly, when we have to perform n comparisons, then how much data would be left to us? N divided by 2 raised power k, because we can see it from here, it's 2, then it is the power of 2, it is a power of 2 again, it is a power of 2 again. That is the reason why when we perform n comparisons, because this is what we are generalizing over here, we don't know what n is equal to. N can be 5 elements, we can have 10 elements, we can have 1000 elements, we can have lakhs of elements in lakhs. So that is the reason why we let the variable k would represent how much data elements are left to us. Now this is how can we calculate the worst case and the average case? The formula, from this, that means from when n is equal to comparisons, n divided by k, we have to make this, we have to generalize this and make this into the equation. And that in order to make an equation, we have to equal it to 1. So this will be 2 to the power k is equal to n. Then take log both sides, or take log base 2 both sides, doesn't matter as I have shown both cases over here. So when we take log both cases, or log 2 both cases, this is what we get. And as I told you, this k would be a constant, and constants, whenever we calculate time complexities, we don't consider constants. So that is the reason why we only have to take this part of the equation as the worst case or the average case of the binary search, that is equal to log to the base n, or log of n. Like we can write it big O of log n, or big O of log base 2n. This means you can divide log n times until you have everything divided, which means you have to divide log n until you found your element. In conclusion, we are now able to completely describe the computing time of binary search by giving formulas that describe the best, average, and worst case. For successful search, the best case of binary search would be big O of 1. For average case, it will be big O of log of n, or for worst case, it would be big O of log of n. Okay. And for the unsuccessful search, for all the cases, for best, average, and worst cases, it will be log n. So best case mein we only have to perform one comparison. In the worst case, the item x does not exist in the array A at all. Though each iteration of binary search, the size of the admissible range is halved. This halving can be done ceiling log n times. The ceiling log n comparisons are required, and in the average case, big O of log n comparisons to find the average case. Take the sum of all the elements of the product of number of comparisons required to find each element, and the probability of searching for that element is this. So this is in the tabular form of the linear search and the binary search, best cases as well as the worst cases. Hope you understood this. Thank you so much. Have a nice day.